Hi everyone, my name is Isabella. I study physics and math at Columbia University, and I would talk about a very particular tidal disruption event that can improve our understanding of how black holes swallow stars. I will first explain what a tidal disruption event, or TDE, is, and why this particular TDE is so interesting. Then I will describe the instruments and methods we use to analyze the X-ray emission of the source, our results, their meaning, and future plans. So when the star gets sufficiently close to a supermassive black hole, the gravitational force acting on one end of the star will be significantly greater than the force acting on the other end. And when the difference is greater than the force that keeps the star together, the star will be ripped apart, and about half of this debris will spiral towards the black hole to form an accretion disk. And this is what we call a tidal disruption event. This process results in a bright flare that can be detected by our telescopes. And these events are also very interesting because they allow us to find black holes and to study in real time the formation and evolution of structures we know very little about. The problem is that our canonical model for TDES doesn't quite explain the features we observe. Initially, it was expected that the emission should be due to the hot accretion and should peak in soft X-rays, but we observed TDES in multiple wavelengths. And we still like models that can consistently explain these features. And the reason we are interested in this particular source is that it is a TDE that was first observed in the UV optical and later on in X-rays. Here we can see how the luminosity given in log scale changes over time. And we see that there are three peaks. The first two are in hard X-rays, and they happen approximately 30 and 60 days after the UV optical detection. And we also see that as the UV optical luminosity decays over time, there is a brightening by a factor of almost 100 in soft X-rays, almost 1 year after the discovery, which is this third peak. And in our research, we wanted to understand this very rare late X-ray brightening. So we analyzed X-ray data obtained by XMM, which can probe higher energy bands and provide data of really high quality because of its long exposure time. We analyzed 3 observations covering this energy range. And X-ray has a short exposure time because it moves very quickly. So in this case, we could analyze many observations covering this energy range over a longer time period. And Swift has the lowest background, which allows us to probe higher energies with a short exposure time. So in this case, we combine the data to 3 spectra from 0.3 to about 7 kV. We collected the data obtained by these telescopes, then analyzed the different spectra to find the best fit model. Here on the top, we can see how the luminosity of the source measured by different emissions changes over time. And on the bottom, how the emission in low energy X-rays compares to the emission in high energy X-rays and how this ratio changes over time. By comparing the best fit model of different data sets and time ranges and looking at how the luminosity changes with temperature, we can actually investigate the underlying physics of this quite significant increase in luminosity. It changes by over an order of magnitude. As to our results, we found using the Swift data that at early times, the source was best modeled by a double black body, and at late times using the nicer data by a single black body. And this is consistent with what was found in previous works. But the new XMM observations, which have the highest quality, show that the best fit model is indeed a double black body. Here we can see the data from each of the 3 observations. So each color refers to a different observation. The best fit model is given by the solid curve in each black body component by the dotted curve. And the plot on the left shows that a single black body does not provide a good fit for the data, especially at higher energies. The plot on the right shows that a double black body provides a much better fit and can account for the hard tail. So here we also have the temperature of each of the black bodies, and you can see that the cold black body models the soft part of the spectrum and the hot black body the hard part of the spectrum. We were also interested in how the luminosity changes with temperature. So here we are using the nicer observations, and the data are color-coded based on the goodness of fit. So at low luminosity, there is a high scattering, which is likely due to the background, but we can see that the luminosity overall follows the Stefan-Boltzmann law given by this T to the 4th line, which relates the flux of a black body to its temperature. And this is consistent with the emission from the accretion disk. In conclusion, the apparent transition from a double black body to a single black body is likely because we were not able to detect the hard tail at later times when the source was not very bright because of a low signal to noise ratio at higher energies. And the fact that a black body with a temperature of about 50 eV very well describes the data at later times, and that the luminosity follows the Stefan-Boltzmann relation is consistent with delayed accretion. But we still need to further investigate what is happening in higher energies to explain the origin of this hot black body, which could as well indicate the formation of a corona. But at this point, there isn't much we can say about the hot black body at later times. That was it. Thank you so much.